Hi, everyone. I'm Mahdi, and today I'm happy and excited to share our work on Weave, a system for efficient and expressive oblivious analytics. This is a joint work with my colleague Grace and my advisor Anurag Khandelwal at Yale. Our work studies MapReduce, the backbone of large-scale data analytics. In MapReduce, mappers process input data into key-value pairs, and reducers compute the final output for each generated key. The shuffle phase transfers records from mappers to reducers based on their key, where all records with the same key end up on the same reducer. We focus on secure MapReduce in private cloud deployments like AWS and Azure, which are used in sensitive fields like healthcare, finance, and law, where users require confidential executions of jobs on highly sensitive data. To ensure this data privacy, these frameworks encrypt data at rest, process them in secure enclaves like Intel SGX, and also even encrypt them in transit. Typically in these settings, the cloud provider itself is assumed to be the adversary, operating under an honest but curious threat model. That is, the cloud faithfully executes user jobs, but observes data traffic to try and infer private user data, such as patient information. Unfortunately, many recent work have shown that such an adversary can infer the identity of private user data solely by monitoring just the encrypted traffic between mappers and reducers. Let's understand the foundations of such access pattern leakage through a simple illustrative example. Consider a disease data analytics task, where a researcher wants to aggregate patient records by their disease using data from 2018 to 2020. The dataset includes 3 diseases: flu, asthma, and COVID. We assume that the adversary in this setting has publicly available knowledge about the input data, such as expected distribution of diseases, and flu being the most common. Also, the temporal skew in the dataset, where COVID records appear only from 2020 onwards. The adversary can observe the traffic between mappers and reducers. However, the traffic is encrypted. So the adversary's goal is to identify disease corresponding to each communicated encrypted record using just the volume of traffic across mapper-reducer pairs. To this end, we identify 2 kinds of access pattern leakage. The first one is distribution-based. That is, the distribution of traffic volume across reducers depending on the input data. The adversary exploits this leakage, for example, by mapping the reducer, which is receiving the most records, R1, to the most common disease, which is flu. The second component is order-based leakage. That is, mapper outputs depending on the input data ordering. For example, reducer 3 here receives records only from mapper 3. The adversary exploits order-based leakage and infers that these are COVID records, since they appear only in 2020. Beyond this simple example, many recent studies have shown that it's possible to fully reconstruct the private data using access pattern leakage. Preventing access pattern leakage and the reconstruction attacks requires obliviousness, which is in our setting, translating to making the traffic patterns independent of the underlying dataset, or more specifically, preventing distribution-based leakage and order-based leakages that we introduced in our simple example. Prior solutions to this problem prevent access pattern leakage either through oblivious sort algorithms like distributed circuit sorting, or oblivious shuffle algorithms like Merbon shuffle. Without going into details, both classes of these algorithms rely on data distribution agnostic approaches for obliviousness to ensure privacy. But unfortunately, the same data distribution agnostic approach incurs logarithmic overheads, which can go as high as 44 times for oblivious sort-based methods and 17 times for oblivious shuffle-based methods in practice. Moreover, both of these approaches cannot support full functionality for MapReduce, where oblivious sort-based approaches do not support non-associative jobs like computing of the median, and oblivious shuffle-based approaches do not support sort-based aggregations. These limitations together raise an interesting research question. Is it possible to design a secure solution that achieves a small constant factor overhead without limiting functionality or not? We show that this is indeed possible through our system, Weave, which addresses access pattern leakage through a distribution-aware approach. Weave introduces intermediate workers called weavers. Weavers perform a two-stage shuffle that mitigate the two components of access pattern leakage that we introduced. The first stage, random shuffle, communicates data between mappers and weavers to prevent order-based leakage. While the second stage, balanced shuffle, communicates data between mappers and reducers to prevent distribution-based leakage. With this review, let's cover the details of Weave by walking through its shuffling stages using the same data of our earlier example. In the first stage, random shuffle, Weave first randomly assigns records to weavers. And then it sends them from mappers to weavers. The pseudo-random assignment of records ensures that each weaver has an identical distribution of records, preventing order-based leakage as the first component of MapReduce access patterns. Next, let's see how Weave addresses distribution-based leakage in the second stage, balanced shuffle. Unlike prior approaches, this stage of Weave uses the underlying distribution of records across keys. And then, with distribution awareness, Bean packs real and fake records across reducers, ensuring obliviousness with much lower overheads. Distribution-aware bin packing requires building a histogram of keys across all weavers. However, aggregating the data for such an exact histogram can easily become a scalability bottleneck. Weave avoids this bottleneck and instead builds a sampled histogram, estimating the full histogram and the exact distribution of data, and then shares it with weavers. We sample 1% of records to build a representative histogram, enabling scalability without compromising on security. We provide a formal proof of this in the paper. Next, weavers continue with using the extracted histogram for bin packing of real and fake records, where weavers first assign keys to reducers to balance the number of real records that across reducers for efficiency. After the assignments of real records, fake records are added to each reducer to ensure that each reducer in total receives the same number of records for obliviousness. After the assignment of all records, number of records that each reducer processes is a constant factor multiple of the original input, providing both security and efficiency at the same time. Weave then devises fake distribution creation plan among weavers. Weavers use the casted distribution to append the assigned fake records to the real records of the map output that they have received earlier. And then send the real and fake records at the same time to reducers. You can see that the balanced shuffle stage ensures that the traffic volume on the links follow identical distribution. Also, as seen by the adversary, real and fake records are indistinguishable from one another on the links. Moreover, each reducer receives the same number of records, decoupling traffic volumes across reducer inputs from the underlying data distribution and eliminating distribution-based leakage. Looking at the overheads that Weave adds, we show in our paper that the random shuffle introduces an equal overhead to the insecure baseline, while the balanced shuffle adds another 2 times. This allows Weave to achieve an overhead of 3 times overall, which was the aim of its research question. Weave is formally secure. We analyzed this claim using a real versus random indistinguishability framework. Intuitively, in this framework, the traffic patterns from shuffling real user data in the target system must resemble those created by shuffling random data of the same input size. The adversary then observes and compares the 2 executions. And we say that the target system is secure if the adversary cannot distinguish between the 2 executions. We call this notion of indistinguishability under chosen dataset and job attacks, or IND-CDJA. At a high level, Weave achieves IND-CDJA security as we saw that the traffic distribution across various worker pairs is always independent of input dataset. Weave is implemented within Apache Spark and requires no code modification for existing Spark applications. We have evaluated Weave on 10 to 20 node Azure cloud clusters of secure SGX-based VMs. I will defer the details of evaluations to the paper, but we have evaluated Weave besides OPEC and shuffle and balance as representatives of sort-based and shuffle-based approaches of prior solutions, and also Spark default shuffling as an insecure baseline. Here, we demonstrate the execution times across various jobs. Our key findings are that Weave's constant overhead design results in a mere 40% slowdown over the insecure baseline, making it 6 to 14 times faster than prior secure approaches. Moreover, unlike prior solution, Weave does not limit functionality. For scalability, we will look at how all systems scale as we increase the number of records as well as the number of workers. For scalability with the number of records, Weave's execution time scales linearly due to its constant factor overhead. In contrast, the execution latency of prior approaches grows superlinearly due to their log factor overhead, reaching up to 8.3 to 20.1 times higher than Weave at the largest scale. Similarly, for scalability with the number of nodes, Weave's execution time decreases linearly, while performance of prior solutions improves sublinearly. Presenting those results, I would like to conclude my talk today. I have presented Weave, an oblivious MapReduce framework with constant overhead. Weave uses distribution-aware and noise injection for security and performance. This allows Weave to achieve up to an order of magnitude lower execution time at the scale than prior solutions, without compromising on functionality. Thank you for your time and attention, and I would be glad to open the floor for questions.